Okay. Questions about it? Anything from before?
On the homework page that you just gave us, the B and C, I forget what side's the front, but I was wondering if there's two products, if you have to say if there's two products made, or just include that in the description.
Let's see, B and C.
It's for an ester and then lithium.
It's a cyclo. This is for part one. Or no, sorry. Hold on. Hold on. That was in class problems. The homework problems. So that's the carboxylic acid plus the lithium aluminum hydride.
Yeah.
So with the carboxylic acid plus lithium aluminum hydride, so whenever we think of lithium aluminum hydride or sodium borohydride, what are those basically equivalents of? H minus. So whenever you see those, we're thinking this is H minus. So H minus is like R minus. And so when we reacted a carboxylic acid with R minus, what happened? Deprotonated. So the R minus or the H minus is going to come in and deprotonate that. So what we're going to end up with is a deprotonated carboxylic acid plus H2. And then you end up with the then H plus H2O step. So the final product would really be the carboxylic acid and H2. But what I'm mostly interested in is the carboxylic acid part. So if you would have said carboxylic acid or the deprotonated carboxylic acid, I probably wouldn't give you credit for either one. But the H2 is what would be produced as the H minus deprotonates the carboxylic acid. Right, we did Grignard's last week. I guess what you guys would call the trick question. I don't really think there are trick questions, but if you take and try and add a Grignard to a carboxylic acid, people get so used to taking the R minus and having it attack the carbonyl that you have to take a step back, because this is a strong base and it will simply deprotonate the carboxylic acid so that you'll end up killing the Grignard and you'll end up with the deprotonated carboxylic acid. So the same thing's true here with the H minus.
The carboxylic acid, that's not the final product though, is it?
The deprotonated one here?
No, the one above it.
Yes, that's the final product. Because the way the question's written, it said react the carboxylic acid with lithium aluminum hydride. Oh wait, sorry. Sorry, no. That's the first step. What am I thinking? Okay, I'm just going to edit that out of the tape. So let's start all over again. I don't want to go into the mechanism because we'll get to that. All right, whenever you use carboxylic acid and you use lithium aluminum hydride, the carboxylic acid gets reduced all the way down to the primary alcohol. So that's the final product. The mechanism for that is the deprotonate is first 1H minus deprotonates the carboxylic acid, and then the second H minus attacks, but we're a couple months away from that mechanism. So that's the final product. Katie.
I have a question about that. In the book, it says that there's an H2O. Can you single out that?
You can,
Okay.
but you don't have to.
Okay.
Because, I mean, to balance it out, you're going to have the lithium and the aluminum, and you don't know what those are.
Okay.
So just the alcohol is fine. I'm always looking for the organic product.
Okay.
I'm very rarely looking for the other things.
So then, could you go over A on the back?
A on the back side. So what in terms of the product mechanism?
I just looked at it.
Just the product. Okay. So we're taking ethyl Grignard, and we're reacting an ester of formaldehyde. And so I can tell you that I've left out the propanol as the product. But what's going to happen here is that the minus is going to come in and attack the carbonyl. And I'm going to form an O minus. And so I'm going to form that product. Now, the difference in Grignard reactions is that when you have this group being a potentially leaving group, like esters and chloride, that group will leave. So what happens is, because I don't think I went over this in your class. I know I did in the afternoon. So when the Grignard attacks the carbonyl and forms the alkoxide, this would love to bring this pair of electrons back down and make a carbonyl. And every time it tries to do that. All right, so I'm going to give the molecule, I'm going to give it motive and thoughts and stuff, which it doesn't have, but that's what it wants to do. And the reason it wants to do that is because the carbonyl group is really stable. So the only way it can do that is if something can leave. Now, remember, leaving groupability is based on what? A good leaving group is a weak base. So it's inversely related. Leaving groupability is reversely related to basicity. So what are our strongest bases on the periodic table? We've got a C, an N, an O, an F. We got an H way over here. What's the strongest base? C minus. And with that, H minus. So C minus and H minus are our strongest bases. And therefore, they are the worst leaving groups. So carbon and hydrogen groups will never leave. Period. Okay. So let's just recap. The C minus, the Grignard comes in and attacks the carbonyl, forms the alkoxide. The alkoxide wants to reform the carbonyl group. Can H leave? No. Can ethyl group leave? No. Can OCH2CH2CH3 group leave? Yes. And so, as long as there's a leaving group on there, you will lose the OCH2CH2CH3 group, which will eventually pick up a proton And we form then the ketone where the ethyl group that was the Grignard has now added. So now what happens is the second ethyl group, the second ethyl Grignard, now comes in and attacks that, in this case, aldehyde, so that I end up now with an alcohol where two of the groups that have attached to the what was carbonyl are the same. And so in this case, because I started with this H of the ester, that's a formic acid ester, I'm going to end up with a secondary alcohol. If this was an R group, I'd end up with a tertiary alcohol with two groups being the same. So the final product then is going to be that molecule. So you'll get the addition and then have the leaving group leave when this group is either an ester, or that will also happen if you have what's called a carboxylic acid chloride. So if you have either an OR group or a Cl group, it will leave. Everything else has to stay.
Where did the 2CH3CH2 come from?
That was the original problem. The original problem said two of those. The reality is, if I tried to do 1-to-1, what's going to happen is some of this is going to form, and the second equivalent's going to add there. So I'm going to end up with a mixture of the different products. So by using two, I force it all the way to the end.
During CND, how do you know which carbon the Grignard's gonna attack?
That the back,
The left?
the back C and D.
Oh yeah, CND.
Okay, C and D on the back page.
Yeah.
How do you know that? Well, that was partially what I was going to lecture over today. That I shouldn't have given to you as all more problems. I don't know, you tell me. So I've got, let's see, for C I've got an ethyl group here, the O, C, then I've got an H, and then over here I've got a CH2. And so I'm going to react that with isopropyl Grignard. So where's the Grignard going to add? Carbon A or B in the epoxide? Carbon B, why? It's least sterically hindered. SN2. So the Grignard is going to add to the least sterically hindered carbon in both of those cases. Now D has this. So that's the epoxide in D. So where's the Grignard going to add there? What do you think? B? Sure. What kind of carbon is A? Secondary? What kind of carbon is B? Secondary. Still want to stay with your answer B? Sure. Sounds like you need help. Somebody help her. Do you want to stay with B, David?
It's because the cyclohexyl group is so much bigger than the methyl group.
Right. So even though they're both secondaries, then we can look at the group, and the cyclohexane group is bigger than the methyl. So you're right to begin with. It should add to B. So your Grignard's going to add to B in both cases. And we want to talk about the difference between using acid with the epoxide and then using just a straight, strong nucleophile. And I just want to make sure we're all on the same page. Because using the acid will require us to remember back to the last semester. Right. What else? So then let's jump into that. So let's jump into that. Epoxides. That was the topic for today, and to be honest with you, with the addition of adding a negative nucleophile to the epoxide, this is kind of review, but let's kind of all get on the same page. So my first question is this. I want to know, how do I make an epoxide? Bless you. Got two reagents you can use. How do we make epoxides? Peroxyacid. What's a peroxyacid?
Instead, it's a carboxylic acid, but it has RCOOH.
Like that? Okay, so we can use a peroxyacid in one step. So in that mechanism, what happens? The oxygen of the peroxyacid, because all per means is that there's an extra oxygen, right? Hydrogen oxide would be water. Hydrogen peroxide isn't H2O, it's H2O2. So one of the oxygens here just plops down on top of the double bond and makes the epoxide. Whatever the stereochemistry was in the alkene, it is over here, which I think I've kind of reversed it for some reason. So the stereochemistry of the reactant is the same as the stereochemistry of the product. So if it was cis, it's cis epoxide. If it's trans epoxide. So let me see if I can fix this so that it is correct. So there would be my dash, there would be my bold, there would be my bold on the CH3. Another dash. So with if the cyclohexyl and the methyl group are cis, then in the epoxide they have to be cis as well. So we've got that retention of stereochemistry. I forget. What kind of reaction is that? Is it regioselective? Is it stereoselective? Is it regiospecific? Do we agree with that? Couple heads shaking. It is. So this is one of the examples of stereospecific. What does stereospecific mean?
Either goes 100% cis or 100% trans.
Yes. But what it means is if I change the stereochemistry of the reactant, I get a different product. So what was another example of a stereospecific reaction where if I change the stereochemistry of the reactant, I get a different product? This is retaining the stereochemistry. There was another reaction where the stereochemistry was inverted. SN2. Now you got to be more aggressive than that. You got to be confident in your answer. Even if you're wrong, be confident in your answer. SN2. Do we agree? If I change the stereochemistry of the reactant, do I automatically change the stereochemistry of the product? By inversion of configuration. Yes. So this is a stereospecific reaction. Along with SN2 was our other example of a stereospecific reaction. We hit those at the end of the semester, the end of the first semester. So like many of these things, we've got to review and get ourselves back up to speed. So that's just method 1 to make an epoxide. React the alkene with peroxyacid. Does anybody remember the second method? It's the tougher one to remember. How about I react that alkene with bromine and H2O? What do I get? Okay, what do I add? If I'm adding Br2H2O, what do I get? Ashton?
BR and an OH.
Okay, you're adding a Br and an OH. How? So the Br is going to add as an H+. That's going to be Markovnikov. So the Br is basically going to add like an H+, so we're going to add Markovnikov. Okay, so I'm going to add the Br, Markovnikov, and then the OH, and final thing, cis-trans 50-50. Trans. Why? because I'm adding a Br plus, forming the triangular intermediate. Okay, so it's going to be 100% trans. So that means in this molecule, I'm going to end up adding, since the two R groups are the same, or even if they weren't the same, those two carbons have the same number of hydrogens. It doesn't matter which way I add, so let's go ahead and add a Br here. Let's go ahead and add the OH there with the R group and the other H. So I'm adding the BR-OH trans. Okay, so once I have this molecule, what do I do? How about I treat this with Na plus OH minus? So I'm going to react this with hydroxide. What's it going to do?
It's going to take off the hydroxide is going to take out deprotonate the oxygen.
Hold on. So let's forget about the kicking off the Br. And let's go right to the OH minus is going to deprotonate the OH in the molecule. I like that. So the hydroxide is going to deprotonate that OH minus. And we're going to end up now with this. Although the OH minus could basically do an SN2 reaction with the bromine, that doesn't get us to where I'm going. Because what do I want to make out of this? An epoxide. So now if it deprotonates the OH minus and forms this O minus, what's the O minus going to do? Backside attack that carbon and kick off the bromine. So that now I end up with the final epoxide. Flush. So that's how it's going to go. So those are the two methods. The first is peroxyacid, one step. Second reaction would be to add Br2 and H2O, followed by a hydroxide. Is there a preference? Yeah, peroxyacid. That would be my preference because it's one step. All right. Well, let's see. That's just the way we make the epoxide. But if we're going to react epoxides, we need to know how to make them. So we make them from double bonds. Right? So everybody kind of with me? Yes, no? More review. I'm going to change my molecule here a bit. I'm going to put two methyl groups on the right-hand side. And I'm going to react this with HBr. So I've got an epoxide plus an acid in terms of H plus and Br minus. This could be H plus and water, could be H plus and an alcohol. So what I'm really concerned about here is this is what's called acid, and I'm going to put in quotes, catalyzed, because in this particular case, HBr, the acid is acting as a reagent, not a catalyst. when it's H plus H2O, you do regenerate the H plus at the end. So whenever we use acid, walk me through the mechanism, because ultimately I need to know where does the Br go and where does the OH go. So I'm going to open up this epoxide. So first, what carbon should the Br add to? I hear a B. Agree? Don't agree? We agree it's B? No one wants to go for A? Why B? Okay, so we're going to take this through a carbocation intermediate, sort of. You're right, but remember that the bromine and the OH are going to end up opposite each other. So I'm not going to go through a true carbocation intermediate.
After, like, you would protonate it with the H.
Hold on. Protonate the oxygen with H+. I was going to ask, let's work through the mechanism. So my first step was going to be, what's the first step? Protonate the oxygen. Whenever you're reacting an oxygen, nitrogen species with acid, the first step is always protonate the oxygen. Right? That's the first step. That's the first thing should go into your mind. Oxygen, acid, protonate the oxygen. Okay, let's do that. Bless you. Okay, I've got my protonated epoxide. Next question is, we'll make this more interesting. Get everybody involved.
Hope Scherger.
Hope, here's my question. You got a 50-50 shot. Is the oxygen happy with the plus charge? No. Okay, it's not happy with the plus charge.
Benjamin Kitte.
So here's my next question, Ben. So the oxygen's not happy with the plus charge. It's going to dump that plus charge down to those two carbons, carbon A and carbon B. Okay. Which of those two carbons is going to have the greatest delta plus charge? Another 50-50. Carbon B. Do we agree with that? I see a lot of nodding heads. Why? It's correct. B is going to have the greatest delta positive charge. Why? Because it is more.
Disperse the charge more because it's more substituted.
Because it's more substituted. So if we were to look at the delta plus charges on these two carbons, what kind of carbon is carbon A? And I'm going to put it in quotes because I'm going to put it in quotes because it's going to have like a slightly positive charge. So that carbon, primary, secondary, tertiary, carbon A. Secondary, carbon B, tertiary. So which one of those two carbons is going to want the positive charge more? or better, be able to stabilize it better? The tertiary. So there's going to be a greater delta positive charge on B. Okay. This is the series of steps whenever you protonate an epoxide. When you protonate the epoxide, basically the oxygen's going to want to dump its positive charge down to those two carbons. The carbon that's more substituted will be the one that has more delta positive charge. Why is that important? Sort of a rhetorical question. My last step is going to be for the Br minus to come in and attack carbon A or attack carbon B. Which one is it going to attack?
Because it has a positive charge.
B, because it has the more positive charge. Okay. So whenever we protonate an epoxide, the nucleophile is going to add to the carbon that's more after the epoxide's protonated. What is that more like? SN1 or SN2? What do you think? SN1? You're right. I mean, if you're gonna go down, you gotta go down bold, right? And I don't think I've humiliated anybody yet. Well, I should take the yet away. I try not to do that. Yeah, SN1. Because what's the reactivity of an SN1 reaction based on?
More scared than hindered. Sure.
It's SN1. So you just said SN1, we have a greater positive charge. So SN1, what's going to react faster in SN1? Secondary or tertiary carbocation? Tertiary. Why? Yes. Remember, in SN1, we've got the first step to form the carbocation. That's the rate determining step. So the reaction rate is dependent on the stability of the carbocation. So this looks more like SN1 because that bromine is going to add to the carbon with the greatest delta positive charge because that carbon is the most substituted. So this is going to look like an SN1 reaction. The reason why I say it looks like an SN1 reaction is because I don't have a full-blown tertiary carbocation. If I did, the bromine would add from both sides, and we would end up with the bromine cis to the OH and trans to the OH. That doesn't happen in epoxide. In epoxide, the OH and the Br are always going to be trans because that triangular network is still going to be intact. The bromine has to add from underneath. So when you're using acid, the nucleophile will add to most substituted carbon of the epoxide. That's how we get the regioselectivity of an epoxide opening under acidic conditions. So every time you protonate that O, you force the mechanism, you force the nucleophile to add to the most substituted carbon. And it's still going to be 100% trans. Okay. Everybody okay with that? So we're like just after Thanksgiving. when we talked about that. But we didn't talk about what happens if there's no acid. So we didn't say, well, and I'm going to change the molecule here. I'm going to take away the two methyl groups and just make two H's. So now, let's say that I want to react this with a negatively charged nucleophile. First, no acid. Because of course, if acid's present, the acid reacts with the nucleophile, the negatively charged nucleophile, and it's not a strong nucleophile anymore. So I want to do what I call strong nucleophile epoxide opening. Sometimes they call it basic, under basic conditions. But I'm just going to say strong nucleophile. So now, what's the nucleophile, which carbon is the nucleophile going to add to? I know it's stressful.
Caroline Maltese.
Which one's it going to add to, A or B?
DA. Okay, so
Okay.
Well, if the positive charge added to those substituted, this one's going to add opposite, so PP.
Okay. That's logic. Whether it's the correct logic or not, we'll get to, but it's logic. And it kind of makes sense, right? Because we've kind of paired some reactions up. Well, if you do this, you get this. If you do this, you get the opposite. And this is one of those cases. So yes, it will add to B. Why? Give me a parallel to what we've been talking about, David.
It's less hindered, so
It's less hindered. B is less hindered. I'll buy that. Colin?
It has a less pressure positive charge.
Do I really need to know about the positive charge? You're correct. It does have less of a positive charge, but there's no positive charge there to begin with. So that's the difference. When I protonated it, I automatically forced a +1 total charge on those two carbons. I'm not protonating it this time, so there's just a normal positive charge between the carbon and the oxygen. When I add the H+, these two carbons have a total +1 charge. So I'm forcing a charge on them. When the molecule is just simply the molecule, there's a little bit of charge, but overall there's no charge there. So does that matter? Not as much. So let me ask this question. I'm adding a strong nucleophile. What kind of mechanism am I looking at now? Am I looking at SN1? Nah. SN2? Yes. So now what I've done by using the strong nucleophile is I've changed this to an SN2 mechanism. When I put the +1 charge on the molecule, that was SN1. So now I've got an SN2. Everybody buy that? You're okay with that? Because if you're not, then the next set of reasoning isn't going to work. Right. So I got an SN2 mechanism. What dictates the reactivity in an SN2 reaction? What alkyl halides react the fastest in SN2? Primary, secondary, tertiary? Primary. We all in agreement with that? Why?
because of the nucleophile effect in the
Okay. And so what's the advantage of primary over tertiary? Less steric hindrance. So take away two things, which are review. But anyway, SN1 based on carbocation stability. SN2 based on steric hindrance. So which of those two carbons is less sterically hindered? Of A and B. B. So it's less hindered. So what does that mean? That means that's where the nucleophile is going to add. So nucleophile is going to come in, add to B from the bottom, and that's backside attack. It's going to kick off the O. So then what am I going to make? I'm going to make my C with the H with the O minus here, and then down here my nucleophile will have added trans to where the oxygen ends up.
Would you still get the inversion if you had a color?
Yes. So we still have to add from underneath. So we would get an inversion of configuration here because the nucleophile would be taking the position opposite that. And we normally don't look at that, but we could. What we're normally interested in the fact is that the O minus and the nucleophile are 100% trans. All right, I got an O minus. What do I need to do to it? Then H plus H2O to it, so that then I can make my final product, which is having the OH. I've opened up the epoxide with a strong nucleophile, and that strong nucleophile is now added 100% trans to the carbon that is least sterically hindered. Right, so now that takes us back to the first question of the period, which was when you add a Grignard, which carbon should the Grignard react with in the epoxide? It should react with the least sterically hindered one because it is a strong nucleophile.
Before adding the acid, that reactant, could you use that to make a ketone as well
You make the ketone.
with the O on it? Do it with deprotonate that.
Yes, but not that way. Well, because what can happen, if I try and bring the O minus down, I still can't kick off an H. H's and carbons never leave. So when I get to this step, I could turn that OH into a ketone using the reagents for Wednesday, the oxidizing reagents. But I can't just have the H minus leave. And I'll end with this. Carbons and hydrogens can never leave. I mean, okay, there is a system in organic chemistry, right? Hopefully you've started to see some of the patterns. The biggest pattern is if we take, the 30,000 feet view of organic chemistry, besides it sucks, it's hard, all the other negative things, it does have a system to it. Everything's based on functional groups, and the functional groups are hanging off the alkanes because the alkanes make the skeleton. And so I'm hanging the functional groups off of them and changing them. That's what organic chemistry is about. If carbons and hydrogens were easy leaving groups, they don't act as a skeleton anymore. And so it just willy-nilly, these groups would just undergo SN2 and leave. And there wouldn't be an order to it. There would be no skeleton to hang things off of if the skeleton reacted. So that's why carbons and hydrogens, they don't leave. That's not, I mean, they don't leave because they're super strong bases. But they won't leave. That gives us the order that we need. Otherwise, we're memorizing 11 million reactions instead of a lot less. Right? So, epoxides under acidic, nucleophile adds one way. Basic, it's going to add to the least sterically hindered carbon. Okay, there's a video for Wednesday. There's no homework problem, so you can kind of maybe work your way through the top hats. I'll take your homework problems for today, and then I'll give you all of your graded stuff on the way out.